Okay, so first of all, exam 2 is on Monday. And as far as the topics, I'm open to arguments on this, but this is my thinking. Hear me out. So the topics would be everything up through the end of particle kinetics. I've assigned like the first 2/3 of the problem before today. The next 5 I assigned for today. And we can just spend all of today and all of Friday working on problems, getting ready. I think it'll be okay. But, you know, if anybody wants to make like a formal argument why we should make a softer call than that, that way we can just move on to the next stuff after the test. So I'll open the floor. No, probably not. I mean, as far as the old stuff, there'll probably be 2 questions on the newest stuff that we have done since exam 1. And then half of the test will be like new stuff and half will be old stuff. That's how I think about it. And then as far as, so like I can't test everything. I just think of it as sort of statistical sampling, like I just throw a dart at the board and it lands on, I don't actually have a physical dartboard with topics, but that's the idea. Okay, any questions about that? All right, so today and Friday, I'll take homework questions to start, and then I'll do example problems that are related to stuff on the test. Anybody have any homework problems you want to see?
We can start with 12.
12? Do you have it with you? I didn't bring it. Oh, that's a new one, right? Okay, let's wait on that. So I put up the assignment for today already, but let's just, there's a couple things I want to say about that. So anybody have any questions about the first 10 problems? Okay, do you have that with you? Or Fern, can I use yours? Number 6. Oh yeah, number 6. That's what I want to talk about today. So that's a nice lead in. Any questions other than that anyone wants to see? Okay. The same one. Yeah, that's what I want to talk about, 6 and 7. Okay, well, I'm going to start that then. Okay, so here's the example. So let's say that we have a cart on a roller, a cart on rollers. Let's say that this is 2 kilograms. And then we have this idealized pulley, and there's a cable. This is supposed to be horizontal, connecting it to a hanging mass of 0.5 kilograms. And we want to calculate what's the tension in the cable, given that these things can move and accelerate. And we're going to first do it with the ground, that thing fixed. Okay, so let's put this in like a little room. Okay. So first we'll do it with the ledge stationary. And then second, we'll do it with the ledge accelerating up at 2 meters per second squared. Okay, so in that case, it's like this is in an elevator. Okay, and you do this experiment. So we'll do this kind of experiment, once with the whole system stationary, once with it accelerating up. For an observer inside that room, anybody have any intuition about what we're going to see? This is sort of a funny thing that actually connects to the idea of general relativity, which is kind of cool because all we're doing is classical dynamics. But okay, well, think about this. If you were in an elevator, so this is a simpler example of the same thing. You're in an elevator that's stationary, and you drop an object. What acceleration are you going to see in the object? Yeah, so it's just going to be accelerating down at 9.81 meters per second squared. Now, if the elevator is accelerating up at 2 meters per second squared, what acceleration are you going to see when you drop it? 11.81, okay, down. So the acceleration of the elevator to you is indistinguishable from just gravity getting stronger, okay? And if it accelerated down, it would be the opposite. It would look like gravity got weaker. And there's no way for you inside the elevator to know which one of those two is going on. You think there is because it could be a glass elevator and you'd see all the other stuff still, you know. But that's like a small picture view of, like, if everything's glass and you can see the universe around you, you have no idea whether gravity got stronger or you're accelerating or what. Okay, so if you're accelerating opposite the direction of gravity, it looks like the gravitational field gets stronger. If you're accelerating with the gravitational field, it looks like it gets weaker. Okay, and the same thing is going to happen here. So we're going to see, if you think about the accelerations of these things, when this is stationary, there's going to be one acceleration of the 2 kilogram cart to the left and the 0.5 down. If that thing's accelerating up, they're going to accelerate more. It's like gravity just got stronger, okay? And that's this idea in special relativity that that there's no way to tell the difference between two reference frames, even when they're accelerating, if you consider the fact that you could just have a change in field strength. Well, to us, we're doing classical dynamics. So to us, there's a very clear answer to what's going on. We don't think that the gravitational field got stronger. We just say that we're in an accelerating coordinate system. An accelerating coordinate system is non-inertial, and so we can't use it for Newton's laws. So we have to use relative motion. Okay. All right, so let's do the first one. This is the warm-up part. So part A, we're assuming that that's stationary. And we're going to do free body diagrams. I mean, I think the way to approach a problem like this is just start doing free body diagrams and see what you can calculate. Eventually, if you isolate enough things, hopefully, your number of equations will catch up with your number of variables, and you can do the problem. So free body diagram of the 0.5 kilogram mass. The way to approach this always is deal with the field force, the weight force. So that's 0.5 times 9.81, 4.905 newtons down. And now go around the boundary, look for where the surroundings make contact with it. There's only one place, that's where the cable touches it. And a cable force is parallel to the cable, away from the body. And so that's it for the free body diagram. There's no other contact with the surroundings, so that's it. And now we can go to Newton's second law. Newton's second law says 0t plus 0, negative 4.905 is equal to the mass times the acceleration. Is there anything we know about the acceleration just from the way the problem's set up? Yeah, there's no horizontal. And that's all. So there are a lot of these cases where you're just going to have to pin it down to one axis or the other. Okay, you know the direction of the acceleration. You don't know whether it's positive or negative along that line. But that's okay. The sign will come out in the work. So I'm going to write this as, we're doing the, well, it's not 0.5 yet. That's the mass. And now I'm going to multiply it by the acceleration. So I'm using F equals ma. Okay, so I'm going to write this as the mass times this acceleration, and I'll call this a sub 0.5. The x equation doesn't help, but the y equation tells us that if I rearrange this, we get t minus 0.5 a sub 0.5 is equal to 4.905. I didn't have to rearrange it like that, but the reason I did it is you can't solve for either of those variables. That's one equation with two variables. You can't do anything. And so we're just going to have to set this aside and move on to the next equations we can find. Okay, so I'm just going to put a box around this, give it a name, and come back to it later. It's part of a system of equations that we're going to be able to come up with. Any questions about that? Okay, so now let's do a free body diagram of the cart. So free body diagram of the 2 kilogram. There's the outline. And the forces, there's a weight force of 2 times 9.81, so 19.62 newtons down. And now go around the boundary. There's a normal force. That's a pushing contact from the ground. So it's parallel to the perpendicular to the surface toward the chosen body. That's the rule for pushing contact. I'll call that N. And keep going around, and the only other place where the surroundings make contact with the boundary is the cable force. And it's the same idealized cable going over an idealized pulley, so it has the same magnitude of force, T, as the hanging mass did. Any questions about that free body diagram? And so Newton's second law says negative T0 plus 0, negative 19.62 plus 0N. And now I've dealt with all the forces. And these are equal to the mass, 2, times the acceleration. What do we know about the acceleration of the cart? It's horizontal, so I'm going to write this as A2, 0. One of these equations, the y equation, tells us the normal force. That's not going to end up being useful for what I asked for in this question, but we have it. And then the second equation says negative T is equal to 2A2. Okay, so I'm going to write that out, negative T, and I'm going to put it in the form where eventually we can put this in an augmented matrix for the reduced row echelon form. So negative T minus 2A2 is equal to 0. And I'll call that our second useful equation, 2 star. All right, so now can we solve this as a system of 2 equations? No, because what we still have is these 2 different accelerations, okay? But if you look at this problem, you recognize that those accelerations aren't independent of each other. Um, so think about what happens if this 2 kilogram moves an inch in the positive x direction. What is this going to do? Moves up an inch, okay? And vice versa, if this goes in the negative y direction an inch, this goes in the negative x direction an inch, okay? And if you think of that in terms of time derivatives, think of those motions in terms of time derivatives, it's not too hard to convince yourself that the same thing is true of velocities and accelerations. If this has a velocity in the positive x of 5 meters per second, this has a velocity in the positive y of 5 meters per second, or 6 meters per second squared, an acceleration this way. This one has an upward acceleration of 6 meters per second squared. They're locked together. Okay, so you can always just think of it in terms of, like, as you're trying to make sense out of it in your head, you can always just think of it as like, move this one an inch. Where does this one go? Up an inch, down an inch. Okay, so what that says is the relationship between the acceleration of 0.5 and the acceleration of the 2 is if a 0.5 is 1, a2 is 1. So our third equation then is going to be a 0.5 is equal to a2. They're in different directions, but that's all done into vectors. These are just the variables. And so our third equation I can write is a 0.5 minus a2 is equal to 0. And now we have 3 equations for 3 variables. I mean, you could do it as a matrix with 3 rows and 4 columns, use reduced row echelon form, or you could just do it by substitution. We're not going to get any like big systems of equations yet. So if you solve this by substitution, yeah, so if so we have 3 equations, 1, 2, 3. We have 3 variables, a 0.5, a2, t, and then we have the constants. Well, I guess I'll write it out. So t for the first equation, we have one of those. A 0.5, we have negative 0.5 of those. 0 A2s, and the constant is 4.905. Two star. T's, we have negative 1. A2, we have negative 2. Constants, we have 0. And then 3 star, A.5, we have 1. A2, we have negative 1, 0, 0. And what you get is that A.5 has to be equal to A2. Can someone tell me what those are? Negative 1.962 meters per second squared. And what's T? 3.924 newtons. So the main thing I want you to notice, besides the approach for doing this when you have 2 bodies and you have to build up a system of equations, is from statics, it's easy to get lazy with with tensions and cables with stuff hanging from it, you think like, okay, well, the tension in that cable, I mean, it's just a 0.5 kilogram mass hanging from it. So the tension in the cable is just going to be the weight of 4.905. But the acceleration is what ruins that. In statics, you have P minus this weight is equal to 0, right? So they're equal. That always works out in statics. Here we have a non-zero acceleration, and so you can't assume that. Okay. Everybody with me on that? Any questions about that? Yeah, in dynamics, you just always assume that there is. And then the second thing is, so what's going on? I mean, it's happening just like you would think. We got a downward acceleration of this one and a leftward acceleration of the cart. I mean, it couldn't go the other way, so that makes sense. All right, so now we're going to do it, and like to do numbers 6 and 7 in the homework, you're going to sort of have to modify this a little bit, but the overall approach is going to be the same. Question? Yes.
These are in motion, not the elevator, but
right. Yep. Yeah, this is pulling the whole system down. So, and that's what we got in the accelerations. You know, we figured out that they're accelerating. The hanging mass is accelerating down at 1.962 meters per second squared. Okay, so what's going to happen now when the elevator accelerates up? Well, just like if you drop something in an upward accelerating elevator, it's going to look like gravity gets stronger, okay, to an observer in the elevator. And so what we're going to get for the accelerations measured in this moving coordinate system is that this is going to have a bigger downward acceleration than 1.962. This is going to have a bigger leftward acceleration than 1.962. The thing that's tricky, though, is, well, so where does that 2 come into it? Look at this problem and tell me, you know, where things go wrong. Like, why couldn't we just use this exact same approach? So we still have a downward acceleration of the hanging mass, a rightward or leftward acceleration of the cart. Our free body diagrams stay the same. So what changes in the case that the elevator is accelerating up? Yep. Exactly. So the problem comes that because in using Newton's second law, you have to have an inertial coordinate system. And if we're thinking of these from the standpoint of someone watching them in the elevator, just watching this thing do this, that person does not represent an inertial coordinate system. That's an accelerating coordinate system. Okay. And so, yeah, we're going to have to use relative motion in this problem.
Why can't you just add the acceleration to what you write?
Because
they get to do it all over again.
Yeah.
It's a small change.
Right. So the problem is that we have Newton's second law set up using accelerations that are defined in the elevator's coordinate system. Okay. And you can't set up Newton's second. And actually, the place where it happens really is where we make this assumption that those two are going to be equal to each other. So when you set up Newton's second law, you have to be thinking of your accelerations in a ground coordinate system, an inertial coordinate system. Okay. And what we're going to see is that it's not going to come out just yeah, you might think that it's going to be just 2 meters per second squared bigger or something. It's not going to come out like that. It's more complicated than that. Okay, so the problem comes because the elevator coordinate system is not inertial. It's accelerating. Okay, so we're going to have to think about these accelerations as, an acceleration of, let's say, the 0.5 relative to the ground is the acceleration of the 0.5 relative to the elevator plus the acceleration of the elevator relative to the ground. The acceleration of the elevator relative to the ground is the one that's, if we're talking about, well, the elevator relative to the ground is just 0, positive 2. Okay. And this is what we're going to have to use in Newton's second law. And then the acceleration, same thing with the 2 kilogram. The acceleration of the 2 relative to the ground is equal to the acceleration of the 2 relative to the elevator plus the acceleration of the elevator relative to the ground. And again, this is 0, 2. We're still going to have the same thing where the acceleration of the 0.5 relative to the elevator is 0, I'll call that a 0.5. And the acceleration of the 2 relative to the elevator is a2, 0. If you do the free body diagrams, they look the same. Same as part A. And so I'm going to go just straight to Newton's second law for these two. So Newton's second law for the 0.5. The left side stays the same because the free body diagram stays the same. So we have 0t plus the weight stays the same, 0, negative 4.905 is equal to the mass times the acceleration in the ground coordinate system. So now we have to write this as, we can think of this as 0, a 0.5 plus 0, 2. So I'll write it as 0, a 0.5 plus a 2.
Why does the weight stay the same? Like gravity got stronger.
Yeah, so because when we're doing classical physics, it's very clear to us what's happening. There's no ambiguity about whether it's acceleration or gravitational field. To us, this coordinate system is accelerating. the strength of the weight stays the same. And so no matter what happens, our weight always stays the same. To somebody doing general relativity, there's more of a question about that. Okay, so this is the acceleration vector of the 0.5 relative to the ground. That's using relative motion. Okay. And so the x equation is useless again, but the y equation says t minus 4.905 is equal to 0.5 a 0.5 plus 0.5 times 2, so plus 1. Okay. And so t minus 0.5 a 0.5 is equal to 5.905. So that's our star equation, our first one. We can't solve it just like in part A because it's two variables for one equation. And by the way, if you compare this equation to the one star equation in part A, you can see that what we have is just this constant over here that's bigger now. Well, we got it by saying clearly that it came from that added acceleration, but you can see how that could be interpreted as in another way of thinking about it as an increase in the weight. Okay, and now we're going to go to Newton's second law for the 2 kilogram.
Newton's second law applies in the relative motion equation, but not
Yeah.
always.
It doesn't ever apply in a coordinate system that's non-inertial, and that's why we had to use relative motion for our acceleration here. So we had to express the acceleration of this 0.5 kilogram mass in the ground coordinate system by adding up these two parts. We added these two up. The observed acceleration in the elevator is 0.5 relative to elevator. And then we had to add that to the acceleration of the elevator relative to the ground. Well, it only applies to Newton's second law. You can only use in a ground coordinate system, an inertial coordinate system, and that's the end of it. But you can express the acceleration in the ground coordinate system using relative motion. And so I just took this whole thing and put it in as my acceleration for the ground coordinate system. And then you can do the algebra with it, But yeah, Newton's second law always has to use an acceleration that's measured in an inertial coordinate system. Okay, so now Newton's second law for the 2 kilogram. Let's see, what do we have? I'm going to back up to the free body diagram. So we had negative T0. We had the weight of 0, negative 19.62. The normal force 0n. And that's all equal to the mass, 2 kilograms, times the acceleration. And we need the acceleration in the ground coordinate system. So for us, that's, nope, it's horizontal this time. So for us, that's A2, I just called it that, right? Yeah, A20 plus 0, positive 2. So that's the relative motion equation expressing the acceleration of the 2 kilogram in the ground coordinate system. Again, we have, we can calculate that the normal force is equal to 21.62. That's not going to come into this problem, but you can see that again is consistent with it being as if the weight increased. And then the x equation says negative t is equal to 2a2 plus 0. So we can write that as negative t minus 2a2 is equal to 0. That's our second equation. And now since those the A2 and the A.5 are both measured to an observer inside the elevator, this equation still holds that says A.5 is equal to A2. So our third one says A.5 minus A2 is equal to 0. That's our third equation. And so we can write out this equation again, this matrix again, with equations 1, 2, and 3. And then the columns represent A.5, A2, T, and the constants. Our first equation, we have 1T minus 0.5, A.5, and the constant is 5.905. Our second equation, T's, we have -1, A2's, we have -2, everything else is 0. The third one, A2's, we have -1, A.5's, we have 1, everything else is 0. And so A.5, which is equal to A2, what do you get for that? -2.362 meters per second squared. So that's a bigger downward acceleration than we had when it was stationary. And that's not just because the thing's moving. That's the observed acceleration to somebody in the elevator, because that's what we had to use to get that relationship between how the two move. And then what do you get for T? 4.724 newtons. And what was it in the last case? 3.9 something? Yeah, so in all cases here, the things that you measure that like someone in the elevator measures in their experiment is as if gravity increased. But you get it by recognizing that you can only use Newton's second law with an inertial coordinate system. Right. Any questions about that?
Are we done?
Yeah, we're done. You mean to come up with a total acceleration or something? Yeah, if you wanted to know now what's the acceleration in the ground coordinate system, what would an observer outside the elevator see? You would just take these variable values of the acceleration, plug it back into the vectors from Newton's second law, and it would give you the acceleration vectors, the ground acceleration vectors. But I think all I asked for was the tension. And so you can see that the tension increases because of this. There's one more thing I want to show you so you can take a crack at 6 and 7. So you have this system in 6 and 7 like this. You have the ceiling. You have a pulley attached to the ceiling and a hanging pulley that's attached to a mast. It looks like oh no, I drew it the same way. And this is 20 kilograms. And you have a cable that goes, that's supposed to be vertical. And this is 40 kilograms. When you do the free body diagrams, you're going to isolate the whole hanging piece. Okay, so that's going to have a mass of 20 kilograms. And so the weight force is 196.2. And then the cable makes contact with this in 2 spots, here and here. And since it's the same cable, those both have a force T. And then a free body diagram of the 40 kilogram mass. We have a weight force of 40 times 9.81, so that's 392.4. And then a single cable contact. And do the thing again where you think about, so if you pull the 40 kilogram down, the 20 kilogram goes up, okay? But it's not a one-to-one distance relationship anymore with this problem. If you pull the 40 kilogram down, how far up does the 20 kilogram go? Half as much. Yep. And you can think of it this way. If you pull this down an inch, okay, an inch more cable comes past the pulley over here, right? And that inch of cable that gets added to this side of the pulley has to be taken from over here, the other side of the pulley. But the lengths over here have to keep the same distance, the same length relationship, otherwise one would get slack. So the inch over here has to come from half an inch on this side and half an inch on this side. Okay. And so what you get is that if you have a downward acceleration of 1 meter per second squared of the 40, you have an upward acceleration of half a meter per second squared for the 20. So the acceleration, I'm going to call it the acceleration 20 is negative 0.5 A40. Any questions about that? Because one's going up and one's going down. I mean, if you write them as, so if you write like one has an acceleration of 0 A20 and the other one has an acceleration of 0 A40. That's how I was thinking of it, because you first like figure out that they're both moving vertically, and then and then the negative sign is to make sure that one goes up and one goes down.
I mean, the hardest time
Mhm.
that's right, I can see it, like if I think about it for a long time,
Mhm.
it doesn't, it's wanting to switch those. And
Switch what?
keep wanting to switch them, I put 2 on 40 and, or put the half on 20,
Mhm.
but it in my mind,
Yeah.
it's getting switched.
Yeah. I got nothing. No, I know. I mean, the only way I can think about it is pulling this down an inch, adds an inch to this side. It has to get that inch symmetrically from two. This is a cable coming off this one, otherwise it would be crooked. Okay, so pull this an inch down. It takes away half an inch here, takes away half an inch there. That means it rises half an inch. I am giving a talk at lunchtime in the fireside room, I think that's what it's called, over in the partnership center on sort of simple, yeah, simple bike maintenance. So if anybody wants to see how to get your bikes ready for the spring or whatever, how to maintain your bikes, it's at noon today. So, all right, talk to you later.
Thank you.